In this video, we're going to look at two questions on vector calculations. So, for the first question, two aeroplanes A and B travel with velocities VA and VB, where I and J are unit vectors to the east and north respectively. So, and the values are in units of meters per second. So the first component of the question wants us to find the relative velocity of plane A as seen from plane B. Okay, so my idea is that because if something is relative to the other, so for example, if in this case we want to find the relative velocity of A as seen from B, so it's A from B, then essentially it will be A minus V. So in this case, VR would be VA minus VB, which will be equal to 140 I, and then it's VA minus VB, so therefore this will be minus 185 J. And this will be relative velocity. Now, for the second component of the question, it says when time t is equal to 0 seconds, plane A has position RA is equal to negative 400 I plus 1200 J, and plane B has position RB is equal to 800 I minus 600 J. From the time and distance of the closest approach of the two aeroplanes. So what we want to find is the time when the plane A and plane B are closest to each other. Okay, and it has given us the initial positions of A and B. My idea is that maybe we could use the velocities and then convert it to position. But what we want to find is actually the relative position. Okay, so my idea is that we can find the smallest relative position of A to B or B to A, and then that will be actually very effective, and then we can find the time that A or B arrives at this certain point. So how do you find the minimum? This will be rather complex. Let's first derive some kind of equation or a certain value that might represent the relative position in this case. So first of all, we have VA and VB. So plane A's position, let's say A, the position of A, RA, will be equal to 400 plus 50t for some time t, I plus 1200 minus 125t j. And then B's position will be similar. Let me write this down. So this will be 800 minus 90t plus, this is minus 600 plus 60t. Now, how do you actually find relative position? Then rather simple. We can do either ways. So let's stick with the relative position of A as seen from B. So that will be position of A minus B. And this will be equal to, let's see, so it's minus 400 minus 800. This will be minus 1200 plus 140t plus, and then over here this is 1800, and then this is negative 185. And now, so the next thing we can do, my idea is that we can change this into a polar form, but we don't need the angle, because what we want is just simply the distance. So in this case, in vector form, we can't actually do anything about it in terms of finding the minimum distance. So maybe we'll convert it into like the actual magnitude of this relative position. So this is converted into let's represent it with some kind of variable. Say it's just r. So r squared will be equal to and then what you have to do is simply just derive this. First of all, we have to simplify it. So this could be quite a long equation as seen from the numbers. And then this is minus, okay, I might need a calculator over here. So first of all, this will be 1200 times 140 times 2. So this will be 336,000 t plus, I might know this, so that's 14 squared, so this will be, yes, and then continue. So 18 squared is 324 plus 4 zeros minus, so that's 1800 times 185 times 2. That will be 66630 t, and plus 185 squared. That would be 34225 t squared. And then we have to simplify this. So first let's look at the t squared. So this will be, and no, let's just input the number manually. So this will be 34225 plus this, great. And then afterwards, what we do is continue to simplify this. Four, 6, 8, 0, 3, 0. Great. And then so what I'm seeing right now is a quadratic equation. So from the shape, so because the coefficient is positive, this means that the shape of the parabola or the quadratic equation will be something like this. Let me draw it in gray, so because this is just a sketch. It will be something like this. My idea is that this actually contains a minimum point, which is the turning point right here. And how do you find the turning point? Is along the axes of symmetry, and so we can actually solve the minimum distance from this equation right now. And so the x coordinate, let's say x min is equal to negative b over 2a. Now in this case, this is negative b is 1002,000 over 2 times 53825. And what we get is I won't write the fraction, so 308. Let's say 308. And then we can utilize this to find the y coordinate. And then from the y coordinate, then we can take the square root of it, and then we will find the minimum distance. The question wants us to find the time. Oh, we actually need to find, but first of all, we have to look at the time. So in this case, what is the time? The time is simply 9.308. We actually got an answer. So because this is basically the time for which the parabola is at its lowest point. So this is actually one of the answers. And the other answer we can derive from a y coordinate. So how do we do this? We just have to plug this back into the equation. So that will be 53825 times 9.308 squared minus 1002 times 9.308, and then it's plus 468. Okay, this is a rather large number, and so the minimum y value will be 1670.855. So therefore the minimum distance will be simply the square root of this, which is 129. Let's just say 129 meters. So and this will be the answer to the second part of the question. Now for the second question, it says in this question, distances are measured in nautical miles and speed is in nautical miles per hour. And it's a vector question, so I don't think we need any unit conversion. A motorboat sets out at 2 p.m. from a point with a position vector -4i minus 5j relative to a marker buoy where I and j are two fixed perpendicular unit vectors and travels at a steady velocity, so the speed of magnitude square root of 41 in a straight line to intercept a ship S. The ship S maintains a steady velocity vector I plus 4j at 3 p.m., so the time is different, is at position of 3i minus j relative to the buoy. Okay, so what's given in the question is the positions and the velocity and speeds in the case of the boat. So, okay, and then the first component of the question says the position vector of ship at 2 p.m. So, the first part of the question, and then this is really simple. So, basically, the initial vector, let's say it's x and y for the I and j components, plus the time times the velocity is basically its position vector at 3 p.m. So in this case, from 2 p.m. to 3 p.m. is just 1 hour, and in this case, the speed is nautical miles per hour, so basically it's just multiplied by 1, and this will be I plus 4j is equal to 3I plus j. So therefore, x and y will be 2I minus 3j. Wait, this is minus. Minus j, and then so this will be 5 minus 5j. And then this will be simply the answer for the first part of the question. Now for the second part, I want us to calculate the velocity vector of the motorboat. So, what's given in the question, there are several things. So, first of all, at 2 p.m., the position vector of the boat, and then the magnitude of the speed of the boat. And also from the previous question, we know the position of the boat at 2 p.m. And then what's also very important might be the velocity vector of the ship S. So from these values, what I'm seeing is that the vertical component of their position is the same at 2 p.m. So a basic diagram would be something like this. So at 2 p.m., the ship is at -4, -5, so somewhere like here. And then ship S is at 2 minus 5. 2 minus 5, so they should be at the same vertical height. And then what's given the question is that the ship is moving at 1 plus 4j, I plus 4j, sure. So that should be somewhere in this direction. And so, in order for them to intersect, the boat must be traveling this direction. However, what we know is that there is no acceleration in this question, it's all constant velocity. Therefore, there are vertical components. So let's say it's this is 4j. Then the vertical component of the boat must also be 4j in order for them to stay at the same vertical plane and then eventually intersect in the I direction. So what's given the question is that the magnitude of the speed of the boat is the square root of 41. So basically we can use Pythagoras theorem. So 41 is equal to 4 squared, which is 16, plus vi in the I direction squared. So therefore vi would be equal to the square root of 25, which is 5. And therefore the velocity vector will be 5I in the I direction plus 4j in the j direction. And this will be the answer to the second component of the question. Now for the third component, let me write it over here. It wants us to calculate time of the interception. And in this case, in the I direction, I think my idea is that in the j direction they're always in the same plane, so the only way for us to calculate the time of interception will be in the I direction. So basically we can say when the position of the boat is equal to the position of the ship in the x direction, so in the I direction. So in this case, let's look at the ship. So first of all, the ship in I direction is 2, and then plus its velocity in I direction, which is 1 times t, which is t. This is equal to the position of the boat. So in this case, at 2 p.m., in I direction is -4, plus its velocity vector, which is down here, and in I direction is 5, so therefore it's 5t. And from this, we can basically solve for t is equal to 6, so therefore t is equal to 1.5. Now, we might need the unit for this. So it says in nautical miles per hour, therefore this must be in hours. And this will be answer to the third component of the question.